For decades, dark matter was primarily a field of mathematical elegance, defined by pristine equations. But as we turn on the machines, the raw data from physical detectors is beginning to dictate the terms. Much of the search was built on supersymmetry, which proposed the WIMP miracle. It was a calculation where a particle with electroweak interactions naturally produced the exact abundance of dark matter we observe in the cosmos today. High-precision experiments have now tested the specific energy ranges predicted by these models, and they have returned consistently empty. The broad theoretical possibilities of the 20th century are being replaced by rigid experimental bounds. These bounds are tightening from multiple directions. Deep space observations from the James Webb Space Telescope are providing new data on how matter clustered in the earliest stages of the universe. Simultaneously, direct detection experiments like Lux-Zeppelin, located a mile underground, have yielded massive datasets that show no evidence of dark matter particles where we expected to find them. At the same time, high-energy particle searches at the ATLAS detector are systematically closing the windows where hidden dark sector particles might interact with the standard model. Physicists track these constraints on a parameter space, a map that plots a hypothetical particle's physical mass against its likelihood at interacting with ordinary matter. By combining these limits, we can identify exactly where the dark matter hypothesis remains viable and which versions of the theory have been physically excluded. The standard model of cosmology, lambda CDM, relies on the existence of cold dark matter to explain the large-scale structure of the universe. Cold dark matter provides the gravitational scaffolding for the cosmos, clumping together early in time to pull ordinary matter into the first stars and galaxies. This chart maps the theoretical growth of matter density over time. It describes a slow, hierarchical process where small galaxies form first and gradually merge. Cosmic microwave background data fixes this trajectory, requiring a long, steady climb to reach galaxy formation. Under this model, galaxy formation only begins in earnest when that density contrast reaches a threshold of 1. New data from the James Webb Space Telescope is now testing the limits of that predicted timeline. JWST has observed fully formed, massive galaxies at a redshift of 15, just 300 million years after the Big Bang. This data point directly conflicts with the lambda CDM growth rate. These massive galaxies exist much earlier than the linear perturbation equations predict. Accommodating these early structures requires physicists to consider modified star formation models or entirely new physics to explain how matter clustered so quickly. While cosmology looks at the macro scale, the search for the weakly interacting massive particle, or WIMP, has focused on the microscopic. WIMPs are the primary candidate for cold dark matter because their high mass means they move at non-relativistic speeds, allowing them to settle into the gravitational wells that form galaxies. Direct detection experiments attempt to capture these particles as they pass through Earth, looking for the tiny recoil that occur when a WIMP strikes an atomic nucleus. The Lux-Zeppelin experiment at the Sanford Underground Research Facility uses a two-phase time projection chamber containing 7 tons of liquid xenon to watch for these rare events. The LZ collaboration recently completed a 280-day data run, providing the most sensitive search for WIMPs to date. This chart plots WIMP mass against its interaction cross-section. The latest run found no evidence of WIMPs, excluding everything above a mass of 9 giga-electron-volts. This cuts a massive section out of the predicted parameter space, leaving significantly less room for a standard WIMP. As these direct detection limits tighten, the theoretical motivation for the standard WIMP weakens, forcing the field to look toward more exotic candidates. Where direct detection fails to see space particles, the ATLAS experiment tries to produce them by crashing protons together at nearly the speed of light. ATLAS is now hunting for dark sector physics, the possibility that dark matter only interacts with the standard model through a hidden force. This diagram shows the mechanism. Dark matter particles, chi, communicate with us through a mediator called a Z prime. This requires a hidden gauge symmetry, the U1 prime, which is spontaneously broken, resulting in a dark Higgs boson, represented here as the singlet S. Dark matter must annihilate into this dark Higgs to explain why it didn't overpopulate the early universe. The S then decays into the standard model particles we can actually see. To find this, ATLAS looks for collisions that produce a massive spike in missing transverse momentum, energy that was carried away by escaping dark matter. To confirm the signal, this missing energy must be paired with a visible Higgs boson decaying into bottom quarks. This ATLAS data shows the 95% confidence limit on these interactions. The observed limit, marked by the black line, is now far below the theoretical prediction, excluding a huge range of previously viable cross-sections for these dark sector mediators. By failing to find these signals at the LHC, collider data is forcing the masses of these theoretical mediators into higher, less accessible energy levels. As the search at high masses is squeezed by LZ and ATLAS, focus has moved to the opposite end of the scale, ultra-light particles in the micro-electron-volt range. The leading candidate in this low-mass region is the axion. Axions were first proposed to solve the strong CP problem in particle physics, explaining why the strong force doesn't violate a certain type of symmetry. Unlike heavy WIMPs, ultra-light axions behave like a fluid, naturally forming chord density profiles in the centers of galaxies. This may solve one of the conflicts in lambda CDM. While heavy dark matter predicts sharp, cuspy galactic centers, telescope data often shows these more smoothed-out chord profiles. To find axions, the ADMX experiment uses a haloscope designed to convert these particles into light. This requires near absolute zero temperatures and quantum-limited amplifiers to hear a signal that is incredibly faint and exceedingly weak. Using the Primakov effect, ADMX converts axions to photons in a strong magnetic field. This scan has now ruled out the existence of QCD axions between 1.1 and 1.3 GHz. Even in this low-mass refuge, systematic frequency sweeps are methodically narrowing the possible hiding spots for the axion. When we combine these constraints, the structural tension from JWST, the exclusion zones from LZ, the mediator limits from ATLAS, and the ADMX sweeps, the result is a composite map of what dark matter cannot be. The probability of a simple thermal WIMP existing in a standard lambda CDM framework has dropped to nearly zero. This systematic elimination of candidates is how we refine the search for the missing 85% of the universe's mass. A viable dark matter theory must now simultaneously explain the JWST galaxy data, the LZ null results, the collider limits, and the ultralight frequency sweeps. The identity of dark matter will only be found by pushing into the extreme, unforgiving edges of these new experimental boundaries. The possible parameter space for these particles is smaller than it has ever been, but the data we are using to search it has never been more